Welcome to qnawire.
Okay, in this problem we have a 32 centimeter long tube, specifically a cathode tube. Okay. And we are assuming that we want to have 98% of the particles hitting the screen, coming from here to here. We want 98% of them to hit the screen on the other side without ever colliding with another particle. And this is pretty practical. This is kind of what you want to accelerate particles in a cathode ray tube. You don't want them to deflect and hit the sides. You want them to have a clean acceleration the entire way, or at least most of them. So we're asked to find the maximum pressure to make this happen. So this is a problem about mean free paths, and it's a somewhat complicated argument. So we have to walk through the argument before we even start calculations. So first, let's start with our argument. If we want 98% of all of the particles to go across the ray tube without any collisions, we're saying that there's 2% will have a collision within 30 centimeters. So 2% collision within 32 centimeters. If that's true, it must be the case that 50% of the electrons should have a collision 25 times this 2%. So to have 50% of them colliding and 50% of them not colliding, we take our 2% figure of 32 centimeters, multiply it by 25. Okay. And this is about 8 meters. So follow this step from this step to this step. For 2% to have a collision within 32 centimeters, if we want to have 50% getting a collision, it must be within 25 times 32, which is 8 meters. So this is kind of an operational definition of a mean free path. It's the path that it would take. It's the average path, average length for a particle to have a collision, which a good idea of an average is 50% collide, 50% don't. So this would be a mean free path. It's the length that we would expect at least half of them to have a collision, the other half not to have a collision. So once we have that argument sort of settled, we now have to have two formulas. We need the ideal gas law, PV equals NKT. And we need to have the mean free path formula involving some other quantities. It's 1 over pi r squared, n times v, n over v rather. So from there, we can say that big N over v is just p over kt. We can combine that with the mean free path expression to give us kt over pi r squared p, pi r squared p. And if we assume room temperature, which I believe we can assume for this problem, because we usually do not operate cathode ray tubes at other temperatures, they're just in a room. We can estimate temperature to be about 300 K. And we know everything else about this problem. We can say that the radius of our particles is about 1.5 times 10 to the negative 10 meters. That's a good estimate for a molecule. And our mean free path is just 8 meters, using kind of the argument that we developed in the previous page. Thus, we can isolate P to be KT over pi r squared. I keep saying pi squared, it's pi r squared, of course, times L. And we can plug in numbers. We have the Boltzmann constant, 1.38, 10 to the negative 23 joules per Kelvin. I'm not going to include the units just to keep things a little bit cleaner. Times 300 Kelvin. Pi, the radius, 1.5, 10 to the negative 10 meters squared. Mean free path needs to be 8 meters. When we do the number crunch, we end up with a pressure of 7.3, 10 to the negative 3 Pascal, which in atmospheres is about 7 times 10 to the negative 6 atmospheres. So in other words, if we want to have a nice cathode ray tube where we have minimal collisions and so each particle has a lot of time, a lot of distance to accelerate in, we need to have this tube evacuated. It needs to be roughly vacuum or close to vacuum, right? Because there is no such thing as a perfect vacuum, but this is decent. Very, very small pressure. So that's it.